This is the refrigeration presentation for Group 4. For this experiment, Machine Chillers has developed a cooling system based on a vortex tube that has air as a working fluid for safety purposes. The team has been tasked with modeling the system and determining its capabilities. The goals of the experiment completed in Week 1 were to characterize the vortex tube relationships in steady state, determine the heat transfer at the aluminum load, and find its thermal resistance. In Week 2, the team will characterize the relationship between motor speed and pressure and characterize the heat exchanger and accumulator. From the data collected in this experiment and the upcoming Week 2 experiment, the uncertainties of the system will be determined. The refrigeration experiment setup used in Week 1 was composed of a heat exchanger, accumulator tank, vortex tube, insulated aluminum load, 2 flow sensors at each exit, and several pressure and temperature sensors. These sensors give the system multiple points where data was continuously collected for input pressures of 0, 20, 40, 60, and 80 psi. These sensors were calibrated by recording the ambient temperature and pressure and running the system with no air running through it to get the steady state offsets. The major experimental variables collected for this experiment were temperature, pressure, and fluid flow. In Week 2, motor RPMs will be used to collect the data. These variables were acquired by running pressurized air through the system until it reached steady state and then starting data collection. The shown cycle is called a reverse Brayton cycle or Bell-Coleman cycle. The figures presented show the hardware used in Week 1 experiment. The 2 fluid output shown at the top of the diagram have hot and cold outputs. The left output tube outputs hot fluid and the right output tube outputs cold fluid.
Using the setup, data was collected in the steady state region. The pressure gauge, P3, was used to collect pressure data exiting the accumulator tank. The temperatures at the hot and cold streams were also collected. The temperature of the aluminum block acting as a load and temperature at stage 5 were also collected. The flow rates at the hot and cold end were measured and collected using flow sensors at the end of each exit. The vortex tube data from the steady state region was then plotted. The pressure was plotted against the temperature exiting at the cold end, as well as the hot end, along with the mass flow rates exiting the cold and hot ends respectively. While the data was slightly curved, a linear assumption using York regression was used. To achieve steady state, approximately 20 minutes or 2,500 data points were used for the pressure to adjust from 0, 20, 40, 60, and 80 psi. Using the data, ambient heat transfer out of the block and the thermal resistance were calculated. As the data was collected in the steady state, there was no Q dot load, and Q dot air was the same as Q dot ambient. The data is presented in the table. The theoretical thermal resistance was calculated by first taking the dimensions of the aluminum load block and utilizing its geometry to determine the effective thermal resistance. Then Q dot ambient was calculated. The Q dot ambient values are different than experimental because the effective thermal resistance remains constant in this case despite the pressure within the chamber.
After finding experimental and theoretical thermal resistance of the aluminum load, the team turned to uncertainty analysis. First, the uncertainty of the steady state analysis was found. Error propagation analysis was done on the variables of mass flow, pressure, and temperature. Thus, with this error propagation and these equations seen on the slide, the uncertainty for the energy entering the system, Q ambient, and the total energy transferred into the cold air, Q air, was found. The uncertainty of Q ambient was found to be 0.7669, and the uncertainty of Q air was found to be 0.1636. Due to the system being at steady state, the difference between the energy entering the system and the total energy transferred into the cold air is 0. This calculation was then compared to the sum of the uncertainties Q ambient and Q air, and it was found that the sum, 0.9305, is greater than the difference of 0. The second uncertainty calculated was the uncertainty of thermal resistance. Again, error propagation analysis was used on temperature and mass flow to find the uncertainty of those variables. All constants have negligible uncertainty. As seen on the slide, the uncertainty of thermal resistance was calculated by the equation on the bottom. The result was an uncertainty of 0.4360. These discrepancies between the model and the experiment are likely due to the sensor uncertainty and the error propagation of the instruments used.
This concludes the experimentation and analysis done to present for the refrigeration lab in week 1. The vortex tube relationships were illustrated by the plots, and those behaviors in steady state supported the assumptions made for this lab. The experimental thermal resistance was compared to the calculated thermal resistance using the thermal conductivity, total area, and thickness of the styrofoam used for insulation. The calculated ambient energy differed from the theoretical Q ambient since the effective thermal resistance remained constant in different pressures. The uncertainty analysis demonstrated that the differences between the model and the experiment were likely due to the sensor uncertainty. Looking ahead to week 2, we will be experimentally characterizing the motor speed and the pressure relationship. The parameters of the heat exchanger and accumulator will also be characterized through experimentation. Additional pressures between 0 and 40 psi will be taken as needed to construct a good model of the steady-state relationship between motor speed and pressure. Data collected, including the compressor in experimentation, will be analyzed to evaluate how much energy is being supplied or removed by the combination of the heat exchanger and the accumulator tank. Properties such as the transient heat and energy transfer of the aluminum block will also be characterized. The transient cooling of the load while being cooled by building air and then by the compressor will be modeled. The load material properties experimentally measured in testing will be compared against published values to test the consistency of assumptions and results. The uncertainty analysis for week 2 will include all applicable measurements using the final recommendations for the client's inspired experiments. The uncertainty will also report identification of the source of the discrepancies related to the system in the client recommendation. On this slide here, we have our references, and thank you for viewing our refrigeration lab.